Have you heard of this? PN junction is a minority carrier device. Have you heard of that? Bipolar transistor is a minority carrier device. Current in a PN junction is minority carrier current. What do they mean? All right. So these statements we have heard. Current in a PN junction is a minority carrier current. Current in PN junction flows due to diffusion. Right? Are they correct? You've gone through the lectures on PN junction. Are they correct or not? Not correct? Somewhat correct. Right? Okay, so let's look at this here. This is the picture of a current in a PN junction. Let's look at it carefully. Let's digest it. Right? PN junction here. So we have the current in the N region here. This is the hole current in the N region, the red one here. And this, the holes have been injected into the N region and the holes are recombining. That's why the current is decreasing there. And this current we saw is primarily diffusion current. This is a minority carrier current. Hole current in an N region is minority carrier current and is diffusion. And we know that this is JP is decreasing. The total current has to be constant. So JN must be increasing like this. So this is JN. The sum of JN plus JP is constant. That's the total current here, right? That's the total current. We also saw that we can take JN and break it into two parts here. This JN diffusion. JN diffusion looks like this here. Because we said that this region is neutral. So when I have holes which are decreasing like this, I have electrons also which are decreasing like this. So electrons are also diffusing from left to right here. And electrons diffusing from left to right, which means that the current is negative. So electron diffusion current is here. But the net electron current is positive. So the drift current, which is the sum of JN drift plus JN diffusion, should give rise to the total electron current. So the JN drift is over here. So on the N side, I've shown you all the current components. I've deliberately not shown you the JP drift because that's much smaller. We can neglect it here. So we have JP diffusion, we have total JN, and JN diffusion here, and JN drift. And of course, on the other side, we have this JP that you see here. The holes have been injected, and in the depletion region, we are assuming no recombination, so current is constant. And then the current has come from the P region here, so that's how this is here, right? So my first one was current in a PN junction is a minority carrier current. Okay, so let's take this region here, right here at this edge of this depletion region. Is the current at this edge minority carrier current? Current at this edge here, what is it made of? JN and JP. Is it a minority carrier current? I mean, you can see here JP and JN are comparable. It's not a minority carrier current. Take current anywhere in the PN junction. Suppose I take it here, far away. What is the current? Majority carrier current here, right? So it's pure, in fact, it's pure majority carrier current here. As I get closer and closer, the majority carrier current sort of drops. Minority carrier current increases. But I don't find at any place where the current is minority carriers, right? I don't find it minority carrier. Okay? All right. Let's look at the diffusion. If I look at here, what is the current? Purely majority carrier current. And what is it equal to? It's purely drift current. As I come closer and closer, then what happens? I get both drift component, in fact, is increasing. Plus I get diffusion components. But is there any place where the current is purely diffusive? Total current I'm talking about. It's not diffusive. So what about this statement then? Current in a PN junction is a minority carrier current. Current in PN junction flows due to diffusion. Let's focus on this first. Current in a PN junction is minority carrier current. How do you say that? Let's look at this same diagram here, but I've written the current, right? What is the current sum of? The red one shows the red here, the whole current here at this point, and the blue one shows the electron current at this point here. So the current, if you look at it, when I write the expression for current, is made up of two components. This current is whole current, where it's a minority carrier current. Whole current in N region, and this term refers to electron current here, which is in the P region here. It's also a minority carrier current, right? So when I look at the expression of current, it's made up of two minority carrier current components. Two minority carrier current components. So this is what is leading one to say that, so what would be the correct statement then? Is current in a PN junction a minority carrier current? We said no. At various places you see somewhere is pure drift, at other places is a sum of drift and diffusion, right? At any plane, at any cut line if I take, I don't find a place where the current is purely diffuse. In fact, I may find a place where the current is purely drift, right? Far away from the junction, I may find a place where current is purely drift, but I don't find anywhere if I take a cut line where the current is maybe purely diffusive or purely minority carrier current. I don't find that. So do you want to revise your statement? What would you like to say? Current in a PN junction is a minority carrier current? No, but what would you like to say then? Is that a more appropriate statement? Current in PN junction is determined by minority carrier current. It's not that it is minority carrier current. It's determined by minority carrier current components. Why? If you look at these two, take any plane. Let's take this particular plane here, this edge, right? Xn. What do you find? You find two current components, right? This Jp here, which is minority carrier, plus Jn here, which is majority carrier. Correct? At this plane. Let's look at this particular plane. It's made up of Jp, which is minority carrier, fine, but it's made up of Jn also, which is majority carrier. But what determines the value of Jn? How much is Jn here at this point? Who determines the value of Jn? The value of Jn at this particular point is determined by, is actually this current here. This decides. This is the bottleneck. This decides, for example, the current here decides how much Jn will be at this edge. In fact, if I were to make this region as P plus, if I were to make this P plus, what would happen to this component? It will become 0. And what will happen to this current here? It will also become 0. Who is really controlling this majority carrier current here? Jn. It's actually the minority carrier current here. That is really controlling. So the correct statement is, yes, it is made up of both majority and minority, but the majority carrier current component is actually controlled by the minority component. So the current in a PN junction is determined by minority carrier current components. But at any plane, if I look at it, in general, it's a sum of both majority and minority carrier currents. Can I then, if I say current in a PN junction is determined by minority carrier current, then I can also say minority carrier current, we know, flows primarily by diffusion. Right? We know that minority carrier current here is diffusive. Minority carrier current here is diffusive. So it's the diffusion process which is determining the minority carrier current. And so diffusion is what is causing the minority carrier currents. And therefore, so we can't say that current is diffusive. That's wrong. If I look at current, it has drift and diffusion and all that. But minority carrier current is diffusive. And minority carrier current determines the net current, which flows inside your PN junction, right? Also, if you look at it in a PN junction, why does the current flow in a forward bias PN junction? Why does it flow? At equilibrium, what is happening? Suppose I have Vf equal to 0. What is happening at equilibrium? I have a lot of holes here and a very few holes here. So the holes are wanting to go here. By what process? By diffusion. And who's stopping them? The drift is sort of stopping them. The barrier is stopping them, right? The drift is barrier and electric field and drift are all related together. So that's stopping them. Why does it? And then when you apply a forward bias, what happens? Still, it would like to go by diffusion, but then the opposite process, the drift process, you have reduced, and therefore is the diffusion which propels the holes into the end region and causes the current to flow. So if we look at it qualitatively, fine, yes, diffusion is the driving force. The drift is actually the barrier is opposing it, and the moment you lower the barrier, then the diffusion causes the injection of holes here, and then the holes go and determine the current flow. Okay,